In this lesson, we are going to start with inner product spaces. So let's start by remembering that an inner product is basically the dot product. In a different class, we called that dot product. And um, really, all of chapter six has been about inner products, and we're just now finishing chapter six. It seems a little strange to say that because up until the last several sections have all been all about orthogonality and projections and all that. But remember, all that stuff was based on dot product or inner product. Two vectors were orthogonal if their inner product was zero. We used inner product to come up with formulas for projections and all that stuff. So it really is all still related. But now we're going to talk about basically, well, let's put it this way. All of the inner products we've worked with so far have been within Rn. Okay. It's always been just real basic, not basic, but approachable, concrete vectors. Um, and so today we're going to talk about how the idea of an inner product can be extended to other more abstract vector spaces. Um, and there are lots of different ways to define an inner product. And so maybe that's why dot product is not as appropriate a name anymore. So we're going to talk about how to define an inner product in more abstract spaces, and also to determine whether our definition really, or I guess I should say, what characteristics are required in order for something to be considered an inner product. So an inner product on a vector space V is a function that satisfies the following axioms for all vectors u, v, and w, and for all scalars c. So the notation for the inner product is going to be this little pointed brackets like this. And just for comparison, this first property, the inner product of u and v is the same as the inner product of v and u. This would be like saying that u dot v is equal to v dot u. And of course, that's true. That's one of the properties. The second one is saying that basically, if we were to put this in context of dot product, this would be like saying that u plus v dot w is equal to u dot w plus v dot w. Again, yeah, that's true. We call that the distributive property. So we need that to be true for our abstract vector space as well. This would be like saying that if we did cu dot v, that would be the same as c times u dot v. And again, that was a product that we had for dot product. And this last one is saying that u dot v itself is greater than or equal to 0, and u dot u is equal to 0 if and only if u is the 0 vector. Again, that was a property that we introduced with inner product at the beginning of this chapter, and so we want it true for this abstract one as well. And then a vector space with an inner product is called an inner product space. So that's just what we're going to call it when we have a vector space, and then we also have this dot product attached to, or this inner product attached to it. Dot product is considered the standard inner product, and in fact, we're going to see some inner products within Rn that is not the dot product we've looked at before. So just kind of keep that in mind, is that there's more than one dot product that can be applied to a vector space. If our vector space is Rn, I'm sorry, I should have said there's more than one inner product that can be applied to a vector space. In Rn, dot product is an example of an inner product, but there are others that exist as well. Nearly everything we've discussed for Rn in this chapter carries over to other inner product spaces. So everything we've done in this chapter, talking about orthogonality and orthonormal and all that stuff, we're going to look at how that specific concrete example in Rn could be carried over to more abstract vector spaces and to other inner product spaces. So let's start with an example here. I skipped one here. Let's consider the vector space P2. Remember, that was the space comprised of all polynomials of degree at most 2. So it included linear and constant polynomials as well. And so now for any inner product, we need to define what do we mean by an inner product. And so here's how we would define it. The inner product between two vectors in P2, so we're calling them P and Q, the inner product is going to be basically this big long computation. We're going to evaluate each polynomial at 0 and multiply the results, evaluate 1/2 and multiply the results, evaluate it 1 and multiply the results, and then add all those together. So if I want to find the inner product between 12t squared and 2t minus 1, so that would be p, the inner product between p and q. So we're told to evaluate the first polynomial at 0, which would be 0. Evaluate the second polynomial at 0, which would be -1. If I evaluate the first polynomial at 1/2, we get 12 times 1/4, which is 3. And then if I plug 1/2 into the second equation, we get 1 minus 1, which is 0. If I evaluate the first function at 1, it becomes 12. Evaluate the second function at 1, we get 1. Do all the products, add them all together. And so the inner product of these two vectors would be 12. And just like with dot product, the number 12 doesn't really mean a whole lot to us. There's not really a way to use that 12 to connect the two really, but this is our answer. This is the inner product between these two vectors. And if I wanted to find q, the inner product between q and q, so 2t minus 1, 2t minus 1. Well, once again, let's evaluate at 0. So that would be -1 times -1. Let's evaluate at 1/2, which would be 0 times 0. And let's evaluate at 1. So that would be 1 times 1. Multiply them all, add them together, and we get an answer of 2. Okay, we're going to look more closely at that when you take a vector and dot it with itself in just a minute. Or take the inner product of a vector and itself. We'll look at that in just a couple minutes. Okay, so this is one example of an inner product. Again, it's abstract. I doesn't seem like there's much. It doesn't seem like we need three terms. It doesn't seem like we need the choices of 0, 1/2, and 1 mattered. It sure seems like we could have picked any of them and it still would have worked. Now, I do want to, with these abstract vector spaces, it's kind of hard to answer that question of, i- um, is this a valid inner space or inner space product? But we'll get to that in a minute. Let's now take a look at an inner product defined on R2. So here we have these two vectors u and v, which are both in R2, and we're going to define the inner product as 4 times u1 v1 plus 5 times u2 v2. Now, it's worth just noting that if that 4 had not been there and that 5 had not been there, I'll put those back in a minute. But if those had not been there, notice that this is that standard inner product. That's the dot product, right? Multiply the first components, multiply the second components, add the results. So this is the standard inner product. But as I said before, there are times when um, it is possible to define a different inner product on R2 in this case, and it could still be a valid inner product. So let's take a look at what this looks like. And so let's determine if this is an inner product. Again, there are 4 different requirements. So first off, if I did u dot v and if I did v dot u, would the results give me the same answer? And in this case, I think they would, because that would mean basically just switching these two numbers, switching those two numbers, and that's okay. When you multiply two numbers, the result doesn't change any. So these are equal to each other. I'm just going to put a check. There's not a lot of work to do here. We just need to think about it. If I did, well, I mean, I guess we could write, you know what, let me be a little more rigorous here. Why not? So if I did u dot v, that would be 4u1 v1 plus 5u2 v2. And then using the properties of basically what is that, the commutative property of multiplication, this is the same as 4 times v1u1 plus 5 times v2u2, and that's the same as v dot u. So in this way, we're being more rigorous here and just kind of pointing out that, yeah, the u dot v is the same as v dot u. And I'm sorry, I didn't mean to put dot. I meant to put commas with inner products. And no, that is not a semicolon. I just didn't bother to erase the dots. Okay, the next property is we have to work with u plus v comma w, the inner product of u plus v and w. So let's plug this in. So we get 4 times, oops, that should be equal sign. Nope, come on. Okay, so instead of u1 times v1, it'll be u1 plus v1 times w1, and then 5 times u2 plus v2 times w2. Now I'm using the distributive property of just numbers, right? And so this becomes 4u1w1 plus 4v1w1 plus 5u2w2 plus 5v2w2. And let's see, if I rearrange stuff a little bit, we get 4u1w1 plus 5u2w2, and then 4v1w1 plus 5v2w2. And the observation here is that this first term is the inner product of u and w, and the second term is the inner product of v and w. And again, that's the second property we had to prove, right? This was the first, this was the second. The third property dealt with c times u and v, the inner product of cu and v. So this would be 4 times cu1 times v1 plus 5 times cu2 times v2. Both terms have a c, so I can factor that out, and we're left with 4u1 v1 plus 5u2 v2, and that is certainly c times the inner product of u and v. So we proved the fourth property. The last property deals with u dot itself, or the inner product of u and itself. I keep saying dot, I'm sorry. So this would be 4u1 u1 plus 5u2 u2. And the observation is simply we need this to be greater than or equal to 0. Well, certainly, if you take any real number and multiply by itself, you're going to get positive. This will be greater than or equal to 0. And likewise, this product will be greater than or equal to 0. So the sum is also going to be greater than or equal to 0. And the only way that it would be equal to 0 is if u1 and u2 had both been zeros, which means that u is the 0 vector. So anyway, so we went through all 4 properties of an inner product and showed that they all are satisfied here. This is sometimes called a weighted dot product. Again, it's not the dot product because of the 4 and the 5. But if we weight some of those products, then we call that the weighted dot product. Now let's consider a variation on this. What if we had 4u1 v1 minus 5u2 v2? Let's consider that. Now I want to remind you that if even one of those 4 properties of an inner product fails, then this is not an inner product. And so what we want to notice is actually the first 3 properties are going to work. But what we're going to find now is that if I did u and itself, if I took the inner product of u and itself, I'm going to get 4u1 u1 minus, excuse me, this time we're minus. Come on. Minus 5u2 u2. What I want to point out is that this is not necessarily greater than 0. Um, if u2 is bigger than u1, or actually even that's not even less strict than that, it is possible for us to get a negative answer in this case. Real simple example: if u2 was 1 and u1 was 0, negative number. So the fourth property of an inner product fails. So this is not an inner product. And so what we're finding in this case is that the weighted dot products only work if the weights are positive. Because if one of them is negative, then again, that last property might fail. Okay, let's we went abstract there a little bit with that P2 example. We came back to the R, the more concrete. Let's go back to abstract. Consider the vector space. Now let's remember that this represents all continuous functions on the closed interval from A to B. We saw that a while back when we were talking about abstract vector spaces, but that's what this means. It's all continuous functions that are continuous on the closed interval from A to B. And let's define the inner product between two functions as the integral from A to B of the product of those two functions. And again, let's determine if this is an inner product. So once again, let's try the inner product of f and g. So that would be the integral from a to b of f times g dt. I'm being a little lazy here, not writing the f of t, g of t, but you get the point. This is the integral from a to b. Again, we can just flip-flop that product. And then this gives us the inner product of g and f. So the first property has been satisfied. Second property deals with what if we're doing the inner product of f plus g with h. So the integral from a to b of f plus g times h. This would be the integral from a to b of f times h plus g times h dt. We can split up the integral. Right? That's one of the properties of integration, is the integral of f times h dt plus the integral of g times h dt. And this would be the inner product of f and h plus the inner product of g and h. And so again, the second property has been satisfied. The third one deals with the inner product of a constant times f and g. So the integral from a to b of c times f times g. And again, using properties of integration, we can take that constant and pull it out. And so this would be equal to c times the inner product of f and g, which is what we wanted. Third property has been satisfied. The last one deals with the inner product of f and itself. So this would be the inner product of basically f squared dt, right? The integral of f times itself. And it's worth remembering that f squared is a positive function. And if you integrate a positive function, you're always going to get a positive answer. If you want to think of the integral as the area under a curve, if the curve is always positive, is always above the x-axis, then the area is always going to give you a positive answer. This is greater than or equal to 0. And again, the only way we're going to get 0 this time is if f was the 0 function. It is possible for an integral to be 0 if the area above cancels the area below, but in this case, that's not going to happen, right? Our function, again, we're integrating f squared. F squared is always above the x-axis. So when we find integrals, it's always going to be positive because that region is always above the x-axis. So the fourth condition is also met. So this is another example of an inner product. Okay, now we've defined inner product, but of course, after we did that, after you defined inner product at the beginning of the chapter, we then talked about how to use it for different things. So a lot of the things that we used it for previously can be extended to these general inner products. So first of all, the length of a vector. we before we said the magnitude of a vector squared was the vector dotted with itself. We're going to maintain that, but instead of dot, we're going to say inner product. A unit vector is a vector with length of 1. Fine, that means that the inner product of the vector in itself is just the number 1. The distance between two vectors is the magnitude of the difference, u minus v. Two vectors are orthogonal if their inner product is 0. Again, and that's a big one. That's one we use a whole lot for dot product, and so we can still extend that. So the concept of orthogonality. Now, I do want to caution you a little bit. In Rn, the idea of orthogonal meant perpendicular, meant they intersected at right angles. When that was true when our inner product was that dot product, was the standard inner product. The idea of orthogonal here doesn't really make sense uh, geometrically here. The idea of the orthogonal doesn't necessarily mean that they cross at right angles. Think about that last example with the inner product that was the integral. You could find two functions whose inner product was 0. But then what does it mean for two functions to be perpendicular? Just graphically, that doesn't really make sense. So the idea of orthogonality again now is more general. It's not what we've done before, where up until now, orthogonal meant perpendicular, meant form a right angle, because the vectors we were talking about were actual vectors. They were basically arrows in space. And so those arrows could cross at right angles. Well, now the concept of a vector is a lot more abstract. A vector could be a function, a vector could be a polynomial. And so the idea of orthogonality is also more abstract and doesn't necessarily mean create a right angle, but we still want to be able to talk about orthogonal vectors. Anyway, again, abstract, which means, of course, weird. All right, so let's revisit this example that we saw earlier. Our vector space P2 and defining the inner product in this way, the same two vectors P of t and Q of t. And let's find the length of P and Q just to practice using these extensions of the concepts we've seen previously. So we know that the magnitude of P is the inner product of P and itself. So evaluating P at 0, I get 0. And so I'm multiply that by itself. Evaluating P at 1/2, I get 12 times 1/4, which is 3 times itself. And then if I plug in 1, I get 12 times itself. So we get 9 plus 144, which is 153. Oh, and I'm sorry, that I misspoke at the beginning. That was the magnitude squared. So that means that the magnitude of P would be the square root of 153. So for this inner product, for this vector space, this is how we are defining this is how we're calculating the magnitude of this vector. Again, these inner products are not unique. There are lots of inner products on the same vector space, but based on this inner product, this is the result that we're getting for the magnitude. The magnitude of Q squared, and I think we did this one earlier, but let's just do it again to be safe. We get Q dot Q. So when I evaluate Q at 0, I get -1. When I plug in 1/2, I get 0. And when I plug in 1, I get 1. So I'm getting 2. So that means that the magnitude of Q is the square root of 2. There we go. So there's the lengths of our two vectors. Okay. Oops. That's not the right one. There we go. Let's consider again this vector space, same one we saw before. Let's find equations to find the length of f and the distance from f to g. Okay, so let's think about this for a second. First of all, the length of f would be the inner product of f and itself. And by the way, I say find equations because we don't actually know what f and g are. We're just kind of trying to find ways of figure this out. So, I'm sorry, wait, let me start this over again. We know the length of f, or the magnitude of f squared, is the inner product of f in itself. And so that would be the integral from a to b of f squared dt. And really, there's nothing else we can do. That's about as simple as it gets. And so this tells me that the length of f is the square root of that integral from a to b of f squared dt. That's a pretty weird thing to do. But I mean, the definite integral is a number. At least it would be if we had numbers for a and b and a function for f. So square rooting that number makes sense. And then to find the length of f, or the distance from f to g, remember that is the length of the difference of f and g, so f minus g squared. So the distance we're looking for is that magnitude. Well, that magnitude squared would be f minus g, the inner product of that with itself. And so that would be the integral from a to b of f minus g times f minus g dt. And so this integral, and then of course we square root both sides. And so now we're going to, if we take the square root of that integral, that would represent the distance between those two functions. Now, again, I just want to caution you, the geometric concept of distance that we've talked about in Rn doesn't make a whole lot of sense here. What do you mean, the distance between two functions? Well, if we treat these functions as vectors, we can talk about their distance, and you can't see it, but I'm doing air quotes. But again, the geometric, the visual representation of that distance is a lot more abstract and not really something that we can visualize, or really even matches up all that much with the idea of distance that we know. Let's consider another example here. Now we're considering the vector space, the continuous functions from negative pi to pi. Okay, so a little more concrete here. And we want to define, we're defining the inner product the same as the last one, just now we have endpoints. And we want to show that these two functions are orthogonal. Okay, so remember, orthogonal means we want to show that the inner product is 0. Well, let's calculate that inner product. This would be the integral from negative pi to pi of, and actually, no, I'm sorry, let me just erase, nope. Let's just erase everything because I can actually use actual functions here. This is sine x and cosine x. So again, we want to show that this inner product is 0. So the inner product is the integral from negative pi to pi of sine x times cosine x dx. And so to answer this question, we're going to evaluate this integral. To evaluate this, I want to remind you that there are actually a few ways to do this problem, but probably the quickest is to do u substitution. Let u equal sine x. And so then du would become cosine x dx. I'm not going to write out all the work for the substitution, but what we're going to find is that the antiderivative is 1/2 sine squared x, and we're evaluating that from negative pi to pi. So doing u substitution, that's the result we're going to get. And so this is 1/2 sine squared of pi minus 1/2 sine squared of negative pi. Both of those are zeros, so certainly the answer is 0. So we have shown that these two vectors are orthogonal because the inner product was 0. One more time. What do I mean those two functions are orthogonal? But that doesn't really make a lot of sense in this case, right? It's basically, if we treat them as vectors and if we define the inner product in this way, then the vectors are orthogonal. Again, abstract. In the last example, we'll extend what we've learned about dot product to, or sorry, I'm sorry, in the next example, we'll extend what we've learned about dot product to our function inner space product. Okay, so um, well, let's take a look at this. So if f is in C, okay, so f is some function in our overarching vector space, C of A, B, or whatever. And if W is some subspace with an orthogonal basis U and W, okay, again, that concept of an orthogonal basis is the same. It's just now that U1 and U2 are functions, but the concept of an orthogonal basis is the same. Their span is all of W, and they are linearly independent, and they are orthogonal to each other. So we're going to talk about the projection onto W of F. And it's exactly what we had before, right? It's just instead of dot products, now we're talking about the more abstract inner product. But finding the projection of F onto W, we're going to first use F with U1 and then use F with U2. Using the same formula we've been using, we've seen this in a few different contexts at this point. Um, and by the way, the distance from F to that subspace W is the magnitude of F minus the projection. Okay, so the idea is the same. It's the same. To find an orthogonal basis, we'll use the Gram-Schmidt method process. Same idea, right? If I give you any basis for a subspace, we can use Gram-Schmidt to find the orthogonal basis. Again, same idea as we did before. It's just now it's more abstract and more the way we define the inner product is not just the dot product. All right, so let's take a look at this example, and we're on C from 0 to 1, so a little more concrete here. And we've got these three functions that are defined on that interval, f1, which is 1, f2, which is t, and f3, which is t squared. And we're going to define the inner product the same as we have been for these functions. We want to find the distance from f3 to the span of f1 and f2. Now, I want to point out that the formula on the last slide required us to have an orthogonal basis. So just saying, oh, our basis is 1 and t, that's fine, but that's not an orthogonal basis. In fact, we could show that f1 and f2 actually are not orthogonal under this definition of this inner product. If I were to do f1 times f2, so 1 times t, and then I integrate that, I'm not going to get a result of 0. So it's not going to work. So um, we need to, before we can do anything else, we need to find that orthogonal basis. So let's remember, we're going to let, and we're going to use Gram-Schmidt here. We're going to start by just letting u1 be that first vector, which here is just 1. And then we're going to find u2 by taking f2. I'll just write f2 for the moment, minus the inner product of f2 and u1 over the inner product of u1 and u1 times u1. Okay, and I guess I need arrows here. Okay, so this was, again, this was our formula from last class of when we did Gram-Schmidt. In this case, f2 was t, so I'll put t minus. Okay, I think I might have to do some of these off to the side here. So the inner product of f2 and u1 would be the integral from 0 to 1 of f2, which was t, and u1, which was 1 dt. Okay, if I evaluate this, I'm getting an answer of 1/2. Okay, and then u1, inner product of u1 with itself, would be the integral from 0 to 1 of 1 times 1, which would be t, which would just be 1. Okay, so the top was 1/2, the bottom was 1, and then u1 was 1. So I'm getting t minus 1/2. Okay, so there's these two vectors form my orthogonal basis. Now, just purely out of curiosity, I want to see that they really are orthogonal. So let's actually just verify really quick. U2 or u1 And u2, let's find that inner product. So the integral from 0 to 1 of 1 times t minus 1 half. So I'm getting 1 half t squared minus 1 half t. And if I plug in 0 and 1, I'm going to get 0 minus 0. Perfect. So what we've shown is that these two vectors definitely form an orthogonal basis based on this inner product that we've defined. Okay. Now we need to then, let's see, we need to find the distance from F to W. So we need to next find the projection onto W of F3. So that projection was, let's see here, it was, this is our formula from a couple slides back, the inner product of F and U1 over the inner product of U1 in itself times U1, and this was F3. Okay, plus the inner product of F3 and U2 over the inner product of U2 in itself times U2. Need some arrows. Okay. Let me see. I don't know how much space I'm going to have here, so let me see if I can do some of these on the other slide. Yeah, I'll do it here. Why not? So F3 was t squared, I believe. Yes, t squared. Okay, so the inner product of t squared and u1, which was 1, would be the integral from 0 to 1 of t squared times 1 dt, which would be 1/3 t cubed from 0 to 1, which is 1/3. Okay. We've already found the inner product of u1 in itself, so we don't need to worry about that. The inner product of t squared and u2, which was t minus 1 half, would be the integral from 0 to 1 of t squared times t minus 1 half, which would be the integral from 0 to 1 of t cubed minus 1 half t squared. And so I'm getting 1/4 t to the 4th minus 1/4 t cubed. Evaluate that from 0 to 1, and I'm getting 0. Well, that's nice. That's convenient. So actually, based on that, I don't need to do a whole lot more work here. So the F3 and U1 gave me 1/3. U1 and U1 gave me 1 times 1. Plus, and so if the numerator here is 0, I don't really care what the denominator is. Times U2, I'm just going to get an answer here of 1/3. So the projection onto W of F3 would be 1/3. Interesting. Okay, so now I need the distance from F3 to W. So that means I need the magnitude of F3 minus that projection onto W of F. And I'm going to square it. I'll square root in a minute. I know that this is, well, let me write it this way. It's the magnitude. So F3 was t squared, and then the projection was 1/3. So this is the inner product of t squared minus 1/3 and itself. So this would be the integral from 0 to 1 of t squared minus 1/3 squared. Let me FOIL this out. So we're going to get t to the 4th minus 2/3 t squared plus 1/9. Find the antiderivative. So minus 2/9 t cubed plus 1/9 t from 0 to 1. I'm getting 1/5 minus 2/9 plus 1/9. 1/5 minus 1/9 gives me 4/45. And then finally, the distance that I'm looking for is the square root of that. You want to get really fancy, this would be 2 over 3 radical 5. But either, it doesn't matter. Either one is good. Okay, so we've got our projection. So using this abstract, again, it's harder. It's more of a pain, to be sure. Dot product is definitely easier to eyeball. Here, every single time I need an inner product, I need to evaluate an integral, which is kind of annoying, but it worked out okay. And so we have our answer. So this now represents the distance from F3 to that other subspace. Okay. I also just want to remind you guys that we know, where am I? Sorry. We know that these three functions, the 1, t, and t squared, these three functions form a basis for what do we call that? P2. Okay, that's fine. We've done that a while ago. I'm not taking anything away from that. But if I want to talk about an orthogonal basis, I need to first define the inner product. And because of this inner product that I've defined, these three vectors are not an orthogonal basis. Again, and if I want to start talking about projections and distances, just any old basis doesn't cut it. I need it to be an orthogonal basis. That's why I had to go through this whole process of this Gram-Schmidt. Okay, let's change topics. We're going to touch very briefly here on chapter 7. And so let's actually just double back here to remember how to do this problem here, and where we're given a matrix and we want to diagonalize it. Remember, that means we want to rewrite this as some vector or some matrix P times a diagonal matrix D times P inverse. And this all has to do with eigenvalues and eigenvectors. So let's see here. So to find the eigenvalues, we're going to find the determinant of a minus lambda I. So the determinant of 2 minus lambda, 1, 0, and 2 minus lambda. So when I multiply those, I get 2 minus lambda squared minus 0. So I'm getting 2 minus lambda squared equals 0. And so lambda is equal to just 2. To find the eigenvector, so we have one eigenvalue of 2, that's fine. To find the eigenvector, yeah, okay. So to find the eigenvector here, oh, you know, I'm sorry, I totally forgot. We actually could have answered this question without doing all that work. Remember, if we have a triangular matrix like this one, the main diagonal gives you those eigenvalues. So we could have said from the beginning that the eigenvalues were 0, but that's okay. We just proved it. Yay. To find the eigenvectors, we have to solve a minus lambda I times times x equals 0. So augmented matrix here would be so if lambda is equal to 2, this becomes a minus 2I. So this is 0, 1, 0, 0, augmented with 0, 0. This is a fairly uninteresting system to solve. Basically, this tells me that x2 is 0, and x1 can be anything it wants. And so my solution is equal to the vector 1, 0 times x1. Anyway, the point is, I only had one eigenvector, which means this is not diagonalizable. I should probably express that a little more. Diagonalizable. Okay, can't be diagonalizable. Just again, quick reminder, when in our matrix, in our diagonal matrix D here, the entries in that diagonal were the eigenvalues, which, I mean, having the same number repeated twice is fine. But the columns of P were those eigenvectors. And in this case, we would need two different eigenvectors. We're not getting them. So that means that this cannot be diagonalized. Okay. Not all matrices can be diagonalized, as we just found. This section finds criteria that identifies some matrices that can. This is not all encompassing of how do we know if it's diagonalizable or not just by looking at it. The only way we have definitively for answering that question is finding the eigenvectors. If it's a n by n matrix and you can find n eigenvectors, then it is diagonalizable. And if you can't, if you don't find enough eigenvectors, that it is not diagonalizable. Well, in this section, we're going to look at some criteria that tell us for sure whether something is diagonalizable or not. Okay, so certainly an n by n matrix has if an n by n matrix has n distinct eigenvalues, then it can be diagonalized, okay? If you've got n distinct eigenvalues, each one of them will produce one eigenvector. And so then, again, that means you've got enough eigenvectors, which means you've got enough to create that matrix P. Now we have a new definition, okay? The word symmetric. A matrix is symmetric if A transpose is equal to A, meaning if the entry in row I in column J is the same as the entry in row J column I. Okay, and just a couple of examples just visually to see what I'm talking about here. These are symmetric, right? Now keep in mind, in the main diagonal, those can be whatever they want to be, doesn't matter. But notice that here the -2 and here is another -2. Okay, if I were to take row 1, that is the same as column 1, and row 2 is the same as column 2. The next one, again, the main diagonals, they can be anything, doesn't matter. But these two have to be the same, these two have to be the same, and these two have to be the same. And again, some examples that are not symmetric. Listen, as soon as these two numbers are different, it's not symmetric. As soon as these two numbers are different, or these two numbers are different, not symmetric. And symmetric only makes sense for a square matrix. So in this case, if I were to find A transpose, not only would it be a different matrix, it's going to be a different shape. And so that also would not be symmetric. Okay, here's why we care. Let's remember an orthogonal matrix P. We talked about this a couple of videos ago. I can't even say the word. An orthogonal matrix P is a matrix in which the columns are orthonormal. Remember, that means the columns, not only are the columns orthogonal to each other, they are also unit vectors. Okay, so orthonormal means that all the vectors are orthogonal to each other and all the vectors are unit vectors. Okay, so an orthogonal matrix, all the columns were orthonormal. And also what we found was if we have an orthogonal matrix, we found that the inverse matrix was the same as its transpose. It was really easy to find an inverse matrix for an orthogonal matrix. All you have to do is find its transpose. Well, we say, one more definition here. We say that a matrix is orthogonally diagonalizable. Oof. A matrix is orthogonally diagonalizable if there is an orthogonal matrix P and a diagonal matrix D such that A equals P times D times P inverse. So please notice that this is the same definition we had for a diagonalizable matrix, but now it's orthogonally diagonalizable because now we've got more restrictions on this matrix P here. P is not only made up of the eigenvalues, it's not only made up of the eigenvectors, sorry, it's made up of eigenvectors that are orthogonal to each other, and they are unit vectors because this has to be an orthogonal matrix. Please notice, by the way, really quick observation here. If P is an orthogonal matrix, that means that it is also true that A is equal to P times D times P transpose. Because again, if P is an orthogonal matrix, P inverse is the same as P transpose. So it's just worth remembering here. Okay, a matrix is orthogonally diagonalizable if and only if it is symmetric. Well, that's interesting. So the only matrices that are orthogonally diagonalizable are the matrices that are also symmetric. Okay, those are the same thing. Diagonalizable, symmetric, or excuse me, orthogonally diagonalizable and symmetric mean are interchangeable. They are the same thing. If a matrix is symmetric, it is automatically orthogonally diagonalizable. We don't have to check. We know it right away. Um, and some non-symmetric matrices can be diagonalized. Okay, actually, I'm not going to say some. Lots of them can. Okay, lots of matrices, lots of non-symmetric matrices can be diagonalized. We've already seen a bunch of them, but there's no quick way to check this, right? We can't just look at it and say, oh, it's diagonalizable or not, right? We have to go through and find the vectors. But if you look at a matrix and say it's symmetric, well, right away, it is automatically diagonalizable. And not only that, it is orthogonally diagonalizable. Okay, that matrix P is an orthogonal matrix, not just any old matrix. Okay, let's orthogonally diagonalize. Boy, I got some big words here. Let's orthogonally diagonalize this matrix. And I'm just telling you to give us a head start. The characteristic equation is 0 equals the opposite of lambda minus or lambda plus 2 times lambda minus 7 squared. Okay, orthogonally diagonalize. So let's quickly observe A is symmetric. So right away, I'm giving you a job that actually can be done as opposed to one that can't be. So certainly my eigenvalues are -2 and 7. Great. Let's start with -2. Let's solve the equation. Now remember, it's A minus lambda I. So A minus -2i times x equals 0. So I'm going to add 2 to just the main diagonal. And so we get 5, -2, 4, -2, 8, 2, and 4, 2, 5. I'll augment that with 0, 0, 0. Okay. Okay. I'm going to rearrange stuff a little bit. I'm going to switch the first and the second row. So this becomes 5, -2, 4, 0, and 4, 2, 5. But the other thing I'm going to do is when I put that row on top, I'm also going to divide that row by -2. So it becomes 1, -4, -1. Just to make it easier to work with. Okay, multiply the top row by -5 and add the second row. So we get 0, 18, 9, 0. Cool. Multiply the top row by -4 and add the bottom row. I get 0, 18, 9, that's 18, 9, 0. Okay, that makes life easier. The bottom row becomes all zeros. Top row is 1, -4, -1, 0. And the middle row is going to be 0, 2, 1, 0, divided everything by 9, excuse me. And I'm going to, because I need this to become reduced echelon form. So now I'm going to, middle row is fine. Multiply the middle row by 2 and add the top row. I get 1, 0, 1, 0. Apparently I'm working binary here. So this tells me that x1 is equal to -x3. x2 is equal to -1/2 x3. And x3 is itself. Okay, so writing this as a solution here, we got -1, -1/2, 1 times x3. And last thing, just because fractions are annoying, remember any multiple of this is also a correct answer. I'm going to multiply everything by 2. So we get -2, -1, 2 times x3. So there's my first eigenvector. For the other eigenvectors, let's see if I can squeeze this in. I seriously doubt it, but let's see what happens. So I'm going to do a minus 7I times x equals 0. So let's see here. Subtract 7 from the main diagonal. I get -4, -2, 4, -2, -1, -2. Wait, hold on a second. Oh, that should just be a positive 2. So that's 2. And then 4, 2, -4. Okay. And then augment that with 0, 0, 0. They're all multiples of each other, so I can rearrange this a little bit. And so I'm getting, let's see here, 2, 1, -2, 0, and I'll make all the rest of them zeros. And so I get that x1 is equal to -1/2 x2 plus x3. x2 is itself, x3 is itself. So x is equal to, let's see, so it would be -1/2, 1, 0 times x1, x2, excuse me, plus 1, 0, 1 times x3. And again, just to make life easier, I'm going to multiply this first vector by 2, so it becomes -1, 2, 0. Okay, so I've got 1, 2, 3 eigenvectors. Before we go any further, I need to point out here that I actually made a mistake. That last eigenvector should actually be 1, 0, 1, and I assume some of you guys are probably yelling at your screens for that mistake, and I apologize for that. But we got it fixed now. Okay, so if the problem had said to diagonalize the matrix, we'd be done, right? These three vectors can be used to diagonalize the matrix, no problem. But the problem said to orthogonally diagonalize the matrix, which means just having these three or eigenvalues is not, or eigenvectors is not enough. We need to have vectors that are also orthogonal to each other. So we're going to take these three vectors, which I mean they're independent, they form a basis for R3, but what we need is for them to be orthogonally be an orthogonal basis. Okay, so I'm going to give these names. I'm going to call this one Z1. I'm going to call this one Z2, and I'll call this one Z3. And let me write these on the next screen here. So we have Z1 was -1, 2, 0. Z2 was 1, 0, 1. And let's see, Z3 was -2, -1, 2. Okay, so there's Z3. Okay, so we need an orthogonal basis. So I'm going to let V's, so these are my Z's, so I'm going to let V be my orthogonal vectors. So V1 is going to be just that first vector, -1, 2, 0. That's fine. V2, by the way, to find this orthogonal basis, we're using Gram-Schmidt. We're using the same process we did before. So V2 is going to be Z2 minus Z2.V1 over V1.V1 times V1. It should be mentioned, by the way, we're back in R3. We're back to the plain old dot product that we've been using throughout. Okay, we're not worried about any other kind of made up inner product. So Z2 is, wow, I wrote that completely wrong. That's amazing. I wrote it actually exactly opposite of what it's supposed to be. 1, 0, 1. That's awesome. Okay, so Z2 is 1, 0, 1 minus, all right, Z2.V1 would be -1 plus 0 plus 0. So that's cool. That's nice. v1.v1 would be 1 plus 4 plus 0, which is 5, times v1, which was negative 1, 2, 0. So if I put all these together, I'm going to get, let's see, negative 1/5. No, I'm sorry. It'd be 1 minus 1/5. So that'd be 4/5. Now I'm second guessing myself. Lovely. 1 minus 1/5 is 4/5. Yep. And then we get positive 2/5 and 1. Okay. And as we did before, I'm just going to multiply everything by 5. So my second vector here is going to be 4, 2, 5. Let me double check really quickly because now I'm second guessing myself. If I do v1.v2, I'm going to get negative 4 plus 0. Awesome. Orthogonal. Perfect. Now, here's something that's going to be really useful to us. I want to point out that v3 can actually just be z3. It can just be that third vector without doing anything to it. I'm not going to get into why, but it actually does work out. Notice if I were to do v1.v3, I'm going to get 2 minus 2 plus 0, which is 0. These are orthogonal. And if I did these two dot product, I get negative 8 minus 4 plus, I'm sorry, negative 8 minus 2 plus 10, which is also 0. These two are also orthogonal. So it's really nice to observe that we don't actually need to mess around with Gram-Schmidt for the third one. The third one is already orthogonal. And in fact, if we had gone through the process of Gram-Schmidt, all the two terms would have given me zeros. I would have just gotten Z3. Anyway, okay, now I have orthogonal vectors, but I need an orthogonal matrix, which means I don't need orthogonal vectors. I need orthonormal vectors. So now I need to find unit vectors in each of these directions. So divide by the magnitude, so 1 over radical 5 times negative 1, 2, 0. So my first orthonormal vector would be negative 1 over root 5, 2 over root 5, and 0. I really wish I gave myself more space, but oh well. This one, u2. So let's see. Oh boy. Okay, 16 plus 4 is 20. Plus 25 is 45. So square root of 45 times 4 to 5. So I'm getting, let's see, 4 over root 45, 2 over root 45, and 5 over root 45. And this one over here, u3. So, I'm sorry, I need to divide there. So it's going to be 1 over, so it's the square root of 4 plus 1 plus 4 is 9. So actually it's just 1/3. That's nice. No radicals this time. So I'm getting negative 2/3, negative 1/3, and 2/3. Okay, finally, we want to write my vector as P, D, P inverse. Well, let's remember that P, the columns, I'm sorry, that's not what I meant to do. To do this problem, I don't actually have to write it out this way. I basically just have to state what is P and what is D. So let's remember that D was the diagonal matrix where the diagonal entries were those eigenvalues. And let's go way back, and it seems like it's been forever. The eigenvalues were negative 2 and 7. Notice that the 7 repeated twice because of that squared there. So D is going to be negative 2, and I'll just put the 7 twice. There's my diagonal matrix. And now let's just remember, the negative 2 column has to correspond with the eigenvector that went along with that negative 2. So that would be the negative 2/3, negative 1/3, 2/3. And then the 2 columns with 7s correspond with the 2 vectors that came from the 7s. So that would be negative 1 over root 5, 2 over root 5, 0, and 4 over root 45, 2 over root 45, and 5 over root 45. Okay, and again, orthogonally diagonalize means find P and find D. The only hitch is P has to be an orthogonal matrix. Okay, that brings us to the end of our lesson. Thank you very much for watching.